Guys, this next section is on calorimetry. However, I wanted to skip ahead a couple of slides and work a couple of the example problems that make more sense in the context of the previous video, and then we'll save the calorimetry for the next video, I think. So I'm just going to blast through a couple of these slides here real quick, and instead we're going to work this example and the next example, and then we'll get to calorimetry after that. So the slides were just a little bit kind of out of order. So let's start with this. So this builds upon the last video where we learned about the specific heat formula. So in this problem, we're taking a piece of iron metal that is at some elevated temperature, and we're dropping it into water. Okay, so we're dropping a piece of metal that's hot into the water. And what happens is the thermal energy is transferred from the metal to the water. And so as a consequence of that, the temperature of the water is going to increase until the metal and the water are at the same temperature. In this case, the metal is dropped into 425 milliliters of water, and the final temperature of the water is recorded at 42.7 degrees Celsius. They want us to try to figure out what was the initial temperature of the iron, assuming that all of the heat that's exchanged is just between the metal and the water. Okay, so in this problem, we have that the heat of the iron plus the heat of the water must add up to 0. Okay, so that the thermal energy that's transferred from the iron must equal the thermal energy that's transferred from the water, and they'll be equal and opposite. And so they both add up to 0. Now we're going to use the specific heat formula that we learned about in the last video to expand these terms. So for the iron, we are going to have that the mass of the iron sample times the specific heat of the iron times the delta T for the iron, which is going to be the final temperature minus the initial temperature of the iron. We'll do the same thing for the water. Mass of the water, specific heat of the water, final temperature of both the iron and the water, minus the initial temperature of the water. Now they've given us the mass, and that all adds up to 0. They've given us the mass of the iron and the specific heat. We are trying to find the initial temperature of the iron, and they've given us the final temperature of the iron in the water. That's the 42.7 degrees Celsius. Now they haven't directly given us the mass of the water, but the density of water is about 1 gram per degree, 1 gram per milliliter. And so if you have 425 milliliters, that's equivalent to, roughly speaking, 425 grams. Okay, and so this is a valid approximation because the density of water is very close to 1 gram per milliliter. So we do know the mass of the water. They give us the specific heat of water, and we know the temperature difference of the water. We know the final temperature of the water and the initial temperature of the water. So what we need to do is solve for the initial temperature of the iron. So we're going to do a bit of algebra on this equation. So I'm going to expand this term here, and I'll move this term to the other side of the equation. So we'll have mass of iron, specific heat of iron times Tf, minus mass of iron, specific heat of iron, times the temperature of the iron initially. We'll put this guy on the other side, so it gets a minus sign. Like that. We'll move this term over, leaving us with this term here by itself. So I'm putting this term on the other side of the equation. That's why it gets the minus sign. Now, to isolate the final temperature of the iron, we need to divide by that coefficient, both sides. So notice that these two factors are the same as they are here, so we're just going to have TF by itself minus mass of water, specific heat of water, divided by mass of iron, specific heat of iron, times TF minus TW. Okay, so we've isolated the unknown, and we can plug all of the numbers that we know into here. So that's going to be 42.7 degrees Celsius. The mass of the water was 425 grams. Specific heat of water, 4.184 joules per gram per degree Celsius. Divide that by the numbers for iron, 360 grams divided by the specific heat of iron, times this temperature difference, the final temperature, 42.7 degrees Celsius, minus the initial temperature of the water, which was 24. Move that over a little bit. Okay, so there's the calculation that we're going to perform. I believe I did this calculation earlier, hopefully correctly, and I got 248 degrees Celsius when I ran that through my calculator. Okay, so these types of problems here, they really test your algebra skills because you have to work with this kind of sort of hairy equation here, and you have to solve it for whatever they didn't give you. So here's one example of that, and then we're going to do another one that's a little bit different right now. So in this problem, we're considering a piece of copper metal, and I think when I let's see here, I missed a piece of information that we need in the problem. I left it out accidentally. The specific heat of copper is 0.385, so we needed to look that up. So consider this to be part of the problem. So we've got a 248 gram piece of copper. This is the specific heat of copper. It's initially at 314 degrees Celsius, and then it's dropped into 390 milliliters of water. That's initially at 22.6 degrees Celsius. Assuming that all of the heat transfer occurs between the copper and the water, calculate the final temperature of this copper and water. So it's the same setup. You've got the heat that's lost from the copper is gained by the water, and so those add up to 0. We use the specific heat formula, mass of copper, specific heat of copper. This will be the final temperature that we're trying to find, minus the initial temperature of the copper that we're given. That's the 314 degrees Celsius. We add to that the same expression for the water. Mass of the water, specific heat of the water, final temperature that we're trying to find, minus the initial temperature of the water. All of that equals 0. And so this time we're going to solve for the final temperature. Notice that it's in both terms. So we're going to have to do some algebra, a little bit different of algebra, to get to that unknown. So I'm going to expand each term. So that's the first term expanded. Now I'll do the same thing for the second one. All that equals 0. Here are our unknowns. They're both in these terms, so we need to combine these into one. So what I'm going to do is I'm going to factor out TF from both of them. So I'm going to have mass of copper, specific heat of copper, plus mass of water, specific heat of water, times Tf. And what I'm going to do is I'm going to take these other two terms that are negative, and I'm going to put them on the other side of the equation. So we'll have mass of copper, specific heat of copper, temperature of copper, initially, plus mass of water, specific heat of water, and the initial temperature of water. And so that's what we have next. Now we want to divide both sides by this coefficient, and that's going to isolate the final temperature that we want to calculate. Everything's divided by this term in parentheses. Okay? And so the next thing we need to do is to plug in the numbers and then do the calculation. So the mass of the copper, 248 grams. Specific heat of the copper, 0.385 joules per gram per degree Celsius. Then we want to multiply by the initial temperature of the copper, which is the 314. We'll add to that this term here involving the water. So again, the density of water is about 1 gram per milliliter, so we're going to take that to be 390 grams. We'll multiply by the specific heat of water. And then the initial temperature of this water is 22.6. Like that. So that's the numerator. We're going to divide all of that by mass of copper, specific heat of copper, and then we've got the term for the water. So that's the 390 grams times the 4.184 joules per gram per degree Celsius. Okay. So it's just a matter of running all these numbers through the calculator. So I'm just going to start from left to right at the top. For the numerator, I'm getting something like 66,858. Now I'm going to divide it by the denominator. And I'm getting 38.7 degrees Celsius, which is in between 22.6 and 314. So the number makes sense. Hopefully I did the calculation correctly. I'm pretty sure I did the algebra right. And so this is how you solve these types of classic specific heat problems. I'm going to go ahead and stop this video here, and then we'll pick up with calorimetry in the next video.